try to like give you a general or general and a bit idea and a bit more details about like the different numerical techniques that are used to really simulate the dynamical phase of common envelopes. I'm not going so much into the actual simulations. That will be the talk after coffee. But I really try to like look at the different schemes and how they are different and what's potentially advantages and disadvantages of using them for common envelopes. As always with these things, like there rarely is like a scheme that's really optimal for everything. So it's like good to know which things are like more trustworthy or more accurate in some schemes. That's why you have to be a little bit careful with schemes. Also, I think the background in terms of like hydro simulations and details of numerical schemes and so on is like quite diverse here in the audience. So feel free to interrupt me whenever there's anything unclear or you want like more detailed information about something. Go into more detail. Okay, so just to set the stage, what do we actually want? And so the basic system of equations that we are solving is in like, in its most simple form, a combination of the Euler equations for hydrodynamics and the Poisson equations for etc. And there are different ways of solving them. We need to solve them numerically because the system is so nonlinear that essentially for something like a binary to like if you really want to like look at like detailed internal evolution, it's completely or it's reasonably hopeless to try to do this analytically. Of course, the ideal code that we would like to have is of course accurate. Like doesn't really like help us much if we don't get the correct whatever that means result. We want it to be stable. This is maybe a slightly less obvious point, but that's often so there's often some kind of trade-off between like how accurate your code is and like how stable it is under like general circumstances. Of course, we want it to be efficient so that we can run long simulations with very high resolution, which we will see in a second is in particular important for the common envelopes. Ideally, we want it to be scalable so we can run on like many cores so that it doesn't take that long. Also, these two things usually have a little bit of a trade-off in practice. So like it's much harder to get a very fast code to scale well than to get a code that is slightly slower to at least scale well with more cores. The interesting thing is that like if you write a computing time proposal, it's almost completely about like how scalable your code is and not how fast it is in absolute terms, because this you can actually show while this is some kind of like absolute criteria, and there's essentially no way that computing centers can judge like whether your code is like fast or slow in absolute terms. And then one thing that is like much more important in practice is because like for most of the simulations you need to modify your code somewhere. And so ideally you want a code that's like reasonably easy to understand, to use, and also to extend. So to add additional source terms, additional physics modules, and so on. Okay, of course, I think it's reasonably obvious that we have nothing that's like perfect in all of these points, so you always have to take some compromises. So I will try to like go through what the properties of the different main techniques are and how they. Okay, just very quick outline of the talks. I will first give some very general characterizations of common envelope simulations, like what we are dealing with in terms of scales for the things we can actually run on the computer right now, not necessarily for the thing that we would want to do in the optimal case. And then I will go through the three main methods that are used today to run common envelope simulations, that are smooth particle hydrodynamics, codes, static mesh, or more specific AMR codes, and moving mesh codes. And then okay, let's look at the simulations. And so I've taken these numbers from Sebastian Ullmann's simulations, but like this is they vary a little bit depending on which type of star and which type of system you run. But like as a rule of thumb, I think they're already a good pointer. So if you look at this Can you actually see anything with the contrast? Okay. So if you look at the simulation that was run until 120 seconds from the beginning from the setup, then at the end of the simulation, where you see that so this is the roughly the size of the envelope, and then if you zoom in, you see the two cores quite close together here. Then the size of the envelope is like 500 solar radii here. The distance between the two cores is a few solar radii. At the end of the simulation, the softening, the gravitational softening, that's the scale on which you kind of deviate from the 1/r potential of the cores, so that you don't get get an infinitely large force in the center, is 1 solar radius here. And you actually have to, or one thing that we found out in these simulations is that you actually have to resolve the scale by quite a few cells to get accurate results, in particular to make sure that energy is conserved reasonably well. And so I will come back to this point later. So the radius of the smallest cell here, which is like a not very meaningful quantity, but it gives you a rough idea how far down this goes, is about 100 or so. So if you compare this number now to this number, then you see that the typical dynamical range of in length scales of such a simulation is 10 to the 4 to 10 to the 5 orders of magnitude. And this immediately tells you that you can't run this with a just uniform constant resolution, because then you would need a mesh that's 10 to the 5 cubed or so. And so you need some kind of adaptive resolution, and you need to figure out how to exactly do that. If you the second interesting question, and that often comes, they often come together, but they're still slightly different and have different or slightly different reasons, is time scales. So of course, if you have very large scales and very small scales, then also the kind of time scale on which these things change and in which you need to evolve these cells is very different. But the kind of baseline that's interesting is of course the total simulation time. In this case, the 120 days. Then the smallest time step. So the time step in general is of course determined by the size of the cell and the kind of signal velocity in the cell, which is in a repo just the sound speed. So these cells are in the very center, close to the cores, and so the smallest time step there is of the order is a few seconds. I think check this about 2 seconds. That means that to get to this 120 days in the simulation, you already need to advance your simulation by roughly 2 million time steps, which is already quite significant. Just as for for rough comparison of orders of magnitude, the most expensive cosmological simulations we are running, we can do 20 million time steps or so, which is only a factor of 10 more than this. So this is already quite hard to do, doing a few million time steps. So the simulation has, the specific simulation has 2.7 million cells. What's interesting is that 500,000 of them, which is quite a significant fraction, actually is on rather small time steps. So that are smaller than 16 seconds, while kind of the rest of the about 2 million cells are on time steps. This is mostly then the background cells here are on time steps that are way larger, so they don't really contribute that much for the total effort you need to do in the simulation. It's really mostly the stuff on those time steps that are close to the cores, where you need to resolve the inner binary and the region between the those. Just to give you a rough number, so this simulation run with the repo cost us 200,000 CPU hours. What's interesting is, so these kind of, I mentioned it indirectly here, so in a repo every cell is kind of evolved to 0th order evolved on the time step that's required for the cell, so with a local core criterion. And if we do a rough estimate on how much we save for this type of simulation, then we can estimate if we would ever evolve everything on the all cells on the smallest time step in the simulation, which would be roughly this 2 seconds, then it would be roughly a factor of 10 more expensive. So running these type of simulations, because the time hierarchy and the spatial hierarchy are so deep, you actually can gain a lot from not doing just one global time step for it. But yeah, we'll come to this in a minute, but almost all the simulation codes nowadays support this. And then, last but not least, there's not only hydrodynamics and gravity, but there are, like we have talked at length about these things already, there's different additional physical processes that we in principle would like to model that make the whole life much more complicated. That's radiation transport, that's magnetic fields, that's dust. And I will come back to this a few times. It's quite, like, it seems to be quite important that we make sure that actually angular momentum, in particular total energy, are conserved. Because if you, like we have mentioned this yesterday a few times, if you get like this, the unbinding is often seems to be quite marginal. And so if you have an energy error, an error in the total energy of like 10, 20, 30% or so, that can be more than what you still need to unbind your envelope, right? And what does your result actually mean? Okay. What's quite interesting in this field is that there's like a wide variety of codes used to run these common envelope simulations. That's just like some subset of recent simulations, so I don't claim completeness here. But like there are the different SPH simulations, there are with different codes, there are different AMR simulations, and now there are the also recent moving mesh simulations. It's kind of an alternative to these traditional AMR simulations. Okay, so let's look at like these three types of numerical schemes a little bit more. So let's look at first at smooth particle hydrodynamics. So here, well, first there are like, well, one of the things why, well, there are many reasons to use SPH, but one of the reasons is definitely that there are actually quite a number of efficient codes publicly available that you can just download and set up your own SPH simulation and run it. So how does this work? SPH is a Lagrangian scheme. So what you do is you discretize the mass of your object into particles, and then you evolve the particles from the forces that, by the forces that act on the particle, which for the Lagrangian scheme are pressure, force, and gravity. So you discretize this into particles. So one of the very nice properties of SPH that also make them quite attractive here is that SPH essentially inherently conserves total angular momentum and total energy perfectly. Okay. The reason why it conserves total angular momentum perfectly is, like, at least qualitatively you can think about, is that all the forces between the particles are isotropic, and so that which is not the case usually in mesh codes, so that so because of this you essentially have no deviationless and don't lose anything here. And the conservation of total energy, in contrast to the other codes, is mostly a consequence that you can actually couple the hydro forces and the gravity forces kind of perfectly. Yes?
But does that also include now, if you want to include radiation transport or magnetic fields?
This is first for hydrodynamics plus gravity.
Right.
If you, as soon as you have like any explicit sync terms, of course you don't convert, you don't conserve it anymore. If you add magnetic fields, which is tricky in SPH, but like I will one or two remarks later for this, it's in principle still depends on how you exactly do it, but in principle there's no necessary reason to be not conserved. But we come to this with the grid codes, but that's kind of the conservation of total energy comes from the fact that essentially you just calculate pressure forces and gravitational forces, and you just apply them the exact same way, and so the whole thing is like consistent. It's also the code is also exactly Galilean invariant. It's a Lagrangian method. If you boost, the whole system doesn't change. Yeah, the coupling to gravity is straightforward. You just calculate in addition to pressure forces. With your SPH scheme, you calculate gravity forces, and because so the way this works is you have these like mass particles, and they usually you give them all the same mass. And so then when there are more particles in some area, like you have a higher density there, you have more resolution, and if, like in underdense regions, you just have fewer particles. So you have fewer particles in low density regions, and you have less resolution. So this whole thing is intrinsically adaptive to density, which for common envelope simulations is, at least the first order, a quite nice feature. So we have like a lot of resolution in the center where it's the highest density, and less resolution in the outskirts where less is going. Yeah, so this is just a schematic kind of picture of how you calculate these forces. So the smoothed particle hydrodynamics, the name comes from the fact that to calculate like pressure forces, you kind of have a spherical kernel, and you sum up the contributions from, like you do a weighted sum of the contributions of all neighbors within a certain radius, and then you choose this radius such that the number of other particles in this radius are always roughly the same. So you automatically, if they're further apart in a lower density region, you like smooth over larger scales, and in a high density region you smooth over smaller scales. And so yeah, this is then you just call this the radius of this thing, which we smooth. And so this is then also, this is the typical kind of scale on which your hydro quantities are well defined.
So having higher resolution and higher density, it seems to make a lot of sense, but the part that our observations are sensitive are possibly actually in the low density regions, and I'm wondering, is there freedom to reallocate resolution to places where the observational consequences are strong?
So this is actually one of the downsides of this method. That's like very hard, and in practice I think almost never done, because the artifacts you get from this are dominating usually over the gain you potentially have. So this thing is adaptive to density, but usually only to density. Principally, you could think about like splitting particles or merging particles, but like I think people have tried this a little bit, but it has never worked well enough to actually.
It's usually done by imposing the initial mass resolution with the smallest particles at the place where you want to resolve the best of that. I mean, for example, we have 10 and 4 factor and mass resolution for different types.
Also, you have to be careful. So you can, in principle, vary the mass resolution slowly, but you have to be really careful that you don't get situations where particles of different mass are like close together, because then this weighted sum here is like can get like very one-sided to the massive particles or so, and you can actually also predict that. So that's by, in most cases you can maybe vary the mass by factors of a few, but you wouldn't usually people run it with constant.
I was wondering, are you going to say anything about initial conditions for SPH? I mean, the stability of an initial model depends a lot on how you choose the positions. And
right. So no, I hadn't planned this, but so yeah. So this is tricky in SPH as well, because you need like to get you kind of yeah. Well, let's come back to this in a minute, because I think there are 2 more things that come. Okay, so you do these like averages over the smoothing lengths to calculate, for example. So now there are some also significant downsides of this method, but like it's in general like very stable. One problem with the Lagrangian-ness of the method is that there's also like the method, the kind of simple implementation of the method does not have any way to increase the entropy in shocks, for example. And so what you need to introduce is a so-called artificial viscosity, where you try to heuristically detect shocks and then add entropy there. And you not only need this for shocks, but you also need this for stability, because you always need some non-zero viscosity in any hydrocode, otherwise it will. The problem is that it's very hard to figure or to like do this artificial viscosity such that it really exactly only triggers where you want, right? Because so this means that leads to the problem that you always tend to like dissipate slightly more in regions where you don't really want to and where there's not really anything going on. There are also like nowadays a million ways to do this, and you can go to like very complicated like attempts to find your shocks here. The problem, but yeah, there's essentially you can't do this without, like, or there's no perfect way of that you can play with this a lot. Then a second kind of fundamental issue that also comes to back to the initial conditions problem is there's always significant noise on the scale of the kernel, like on the scale of this smoothing length, because on the to some level the particle integration has some properties of a Monte Carlo integration. It's a little bit better because these particles like move with the flow, so it's like they're kind of there where you want to have them, but there's still a significant amount of noise left, and you see this a little bit. So this is a Kelvin-Hamilton stability. You see this a little bit. The contrast is bad here, where like you just get some amount of intrinsic noise in the simulations that's very hard to beat up. And there's, in general, because the method is really purely Lagrangian, there's no mixing between particles, which sometimes can be relevant if you different abundances or so. Yeah, one thing that has been mentioned before that's actually quite convenient in SPH is that it actually allows for true vacuum boundaries. You can essentially just have your particle distribution end somewhere, and then beyond this is vacuum. This also, or one thing that helps you is that like SPH has a significant amount of surface tension usually, or not significant, but has some amount of surface tension that helps you to keep this boundary stable, so you won't like just fling out individual particles usually. However, the problem is that like the quantities you estimate at the boundary, and Natasha showed this yesterday a little bit, are often just not overly physical, because this, if you look back at this kernel, right? If you at some point just don't have anything on one side, right? You essentially do a completely one-sided estimate of all your quantities, and even though it's stable, you can't trust the hydro quantities that you get. One very convenient result is that SPH has traditionally shown to give like very good results even for rather poor resolution. One of the problems is that it generally converges very slowly. So even though at poor resolution you already get like qualitatively reasonable results, you have to really massively increase your resolution to really improve the results. Yes.
So I mean, I definitely agree with that, of course, but the number of particles in the kernel, I think, you don't want to increase that necessarily. Daniel Price has a nice description of, in his review of the.
I think people have argued about this point a lot, and we can continue this. So I would argue that for formal convergence, at least, you also need to go to infinite number of particles in the kernel. But this is like formal convergence of SPH is actually a very tricky problem. And this is very different to all the mesh codes where you can usually reasonably straightforward show convergence.
I think it was shown that formal convergence is not achievable even with complete number of neighbors, but it's already was applied now.
I think, yeah, okay. Like I think, yeah, it's a long, complicated topic. How, like, to which degree SPH actually converges with it. So keep in mind, it's like really, it's very good at like slow resolutions, but like you have much less of a gain usually by just increasing the particle number mass. And it turns out it's in practice actually quite hard to like add additional physics like magnetic fields or radiation transport, partly because of how you define hydro quantities like the temperature. It's not completely trivial whether you smooth them or take this particle values. And the noise on the mesh scale that you always have kind of makes life with magnetic fields very hard. This noise is also kind of one of the bigger problems with the initial conditions. So you really need to like, ideally a very regular initial particle distribution that you usually also have to damp for a while to really get like, to get a stable kind of hydrostatic initial. Yeah, initial conditions. Okay. So much about SPH. Then let's quickly look at like the kind of other very widely used method here. That's static measure AMR codes. Also here there's quite a number of codes here to choose from. Many of them are open source, so you can just download them and try to run your own simulation. The idea of the AMR adaptive mesh refinement is that you, well, all these codes discretize the volume into cells, so it's like a volume discretization, not the mass discretization that we had in SPH. And so the adaptive mesh refinement now means that you, like, depending on essentially any criteria, you decide that you have that you split a larger cell into 4 smaller cells, and you can then do this in principle recursively until you, depending on how much resolution you and how much effort you do in the cell. Yeah, so this is a finite. Usually, you implement what's called a finite volume scheme. So in the volume of the cells, you track conserved hydro quantities, the mass, the momentum, and the total energy, and then you evolve them with Riemann solvers by calculating for every time step how much of this conserved quantity flows from one cell. Yeah, so the adaptive mesh just splits the cells. Usually, these AMR codes are, or what you implement there is a second order scheme, so that the result or that the solution should in principle converge quadratically with the error should go down quadratically with the resolution. In contrast to the SPH, you can essentially refine on any arbitrary criteria. Right? You can refine on density, and it's definitely an interesting refinement criteria for common envelope simulations. But for example, you can also refine on the pressure gradient or on the density gradient, or just on the very outer layer of your simulation if you're interested in the optical display. Right? So you can more specifically more precisely put resolution. The coupling with gravity is a bit more tricky, and this is where, in my experience, usually the biggest error in the conservation of total energy comes from, and that's technically coming from the fact that the question is how do you exactly couple the gravitational forces to your hydrodynamic solver? And so in the end, there's there are a few ways to look at this. One of them is that if you do the gravitational forces and then have a hydrodynamics flux from one cell to another cell that carries mass, then the potential of this mass changes from the hydroflux, but you do not compensate for this in the energy, right? So suddenly the mass that went from one cell to another is in a different place in your gravitational potential, but there's usually no compensation for this potential energy that you gained or lost, right? So if you have systematic outflows or inflows, you actually will have some kind of systematic error. And you can, again, so the whole thing should converge at second order, so that should, in principle, go down with resolution, but that can quickly get quite expensive, depending on the problem. One other thing with AMR that's a little bit of a problem, I think not so much for common envelope simulations, but I guess AMR experts can tell more about this, is that sometimes the way that refinement works is you kind of hit some criterion that you now want better resolution, and then you refine, right? But then you already kind of were in a state where your resolution was poorer than you would have liked it there, right? And so you can try to kind of do this then more aggressively to just refine earlier, but this of course makes your simulation significantly more expensive.
Usually just refine based on guard cell or ghost cell information as well as the interior of a
right. I think this is mostly a difference to kind of the moving mesh, where the main difference is that usually the part or the cells already come with the interesting stuff. So you still do refinement on top of this, but the refinement is kind of a little bit earlier. This is mostly, in cosmology, this is a much bigger problem, I think. And one thing that's at least a caveat is usually at these boundaries of the resolution, where you have a larger cell that has a boundary to a smaller cell, actually the scheme is not second order anymore, so it drops to first. Which doesn't matter too much if these kind of resolution boundaries are few and far apart, But if you actually like refine a lot in the center or so, and you have lots of these resolution boundaries, you can actually lose quite some cues. It's also obviously not Galilean invariant, because you have like one preferred frame, which is the left frame, where the mesh sits. What's interesting is that there's like one kind of more subtle difference that comes from this compared to the Lagrangian methods, is that your time step, not kind of like the main type step criterion, so the Courant criterion asks like how fast can information travel over the cell, right? And so for a static mesh code, the fastest velocity with which it can travel is the sound speed plus the absolute velocity of the gas in the left frame. Now, in the Lagrangian code, where the resolution element moves with the flow, it's just the sound speed. So your time step that you get here, if you have a significantly supersonic flow or sonic or supersonic flow, can actually be significantly smaller than if you had a Lagrangian. Okay. For common envelopes, again, this is like not a huge effect, because usually the flows are subsonic or sonic. You don't have like any really strong supersonic outflows or so, but this can still give you a factor of 2 or so in time steps, which for more expensive simulations can help if you're faster or can make it move. Yeah, so this I already said already. One of the nice things is that actually the just generally additional terms, because of the regularity of the mesh, are from all the 3 methods by far the easiest to add. Right? Like so, whether it's like magnetic fields and like different solvers or radiation transport or so, usually it's implemented in AMR first, and it's actually the most stable and reasonably straightforward to implement it there compared to its speed pitch or moving mesh. Okay. Then, last but not least, moving mesh. So, moving mesh is kind of, to a degree, in between the static mesh and SB mesh. There's only very few codes until now. There's a repo, there's a Rich, and there's now Manga. Rich, I think the 2D version is open source, and the 3D is available on request.
Everything is open source, just different branches. Everything is open source, just different branches.
Okay. But I only checked the master branch. There was something.
Yeah, that's right.
Okay, so this is open source, and a repo will actually be open source in a few weeks. So we have a kind of code paper for the public release, almost good. And the public version of the code that will be released is actually great. So what's the difference here? So this is also, again, like in the AMR course, it's a Eulerian discretization, so you discretize the volume, but you don't discretize, like the cell doesn't like stay where it is, but it moves with the flow. And so this is done here using a so-called unstructured Voronoi mesh. And so the main important property of this Voronoi mesh here is that it's spanned up by a set of mesh generating points. And so these mesh, so the main kind of definition of this, or the definition of the Voronoi mesh is that for every of these mesh generating points spans up a single cell, and all the volume that's closest to this mesh generating point compared to any other point belongs to the cell. Okay, and so the important, or the kind of the main reason why this so people have tried to do like kind of moving mesh codes in the past, but the main reason why the breakthrough came with the Voronoi mesh was that the mesh actually changes continuously. You can see this here for 2D Kelvin-Helmholtz instability. You see how so you have a shear flow, and you see how at the shear flow the cells slowly shear against each other and change in a smooth way. So while kind of most or almost all of the things that people have tried decades before to get this to work, they usually had the problem that at some point either the mesh would change like kind of spontaneously, and then you would have to do some kind of explicit remapping, or it was very hard to keep the cells roughly round, because in principle it can become elongated, and then the whole accuracy of your hydro server just drops a lot, because if one end of the cell is very far away in one direction and not so much in the other. It just formally you will still have the same order, but the absolute error increases a lot, and so a lot of black magic goes into how to move around these mesh generating points such that the cells always stay roughly on. So the main idea is that the cells adapt to and move with the flow. So the basic velocity with which you move these mesh generating points that span up the cells is just the flow velocity. Let's show this again. And then on top of this, you have some correctional velocity that you kind of do to try to keep the meshes, the cells of the meshes wrong.
Are there some subgrids here, because cells seem to have different?
So this is essentially just taking the gradient. So this is just showing density, and so this just takes the density gradient in the cells to kind of do an assignment of try to reconstruct the density in the cell. So they should always be linear gradients in the cells. Right. So you do a second order scheme. So also to calculate the fluxes, what you do is you have in two cells the base quantities, density, velocity, pressure. Then you calculate the gradients in the cell from the neighbors, and then you reconstruct 2D interface using these gradients. Yes.
So when you say it's an intermediate, so you're allowing material both to flux in and out of cells, but you're allowing the cells the cell boundaries to adjust as well. So that's what we mean by intermediate, because Cartesian, a usual grid-based code, right? It's not always the same mass in a cell. Whereas smooth particle, it's always the same mass, right? Basically.
So in the kind of ideal case, you would have a very small kind of correction velocity, and you would be dominantly have just the velocity of the gas, and then the code is almost Lagrangian. It's still, you have little fluxes over the interface, but you kind of just take them into account, and then this leads to mass exchange and momentum exchange. You can from a conceptual point of view, you can look at this as just kind of calculating fluxes on this static unstructured mesh, and then you have an additional flux that comes from moving the interfaces. It's just that in almost all cases, these two fluxes almost cancel, kind of by construction, because you move the interface such that it moves with the flow. And then you have much lower advection errors and dissipation and so on, because the absolute fluxes are just much. Yes.
Can you talk a little bit more about zones having very different masses, and how that does or isn't similar to if you set up an SPH, a pure Lagrangian calculation with different mass?
In principle, you can in principle move the mesh in any arbitrary, right? So there are better and worse ways, but conceptually you can move it in any way, right? And so you can also, the mass of a cell can in principle increase and decrease by an arbitrary. So what we do then, to still kind of keep the mass resolution roughly the same, is in addition to this, to kind of just following the flow and so on, we also have, like in AMR, an explicit way of refining or de-refining cells. So we can add additional mesh generating points. Usually we do this directly next to an existing one, so that it just splits the cell in two. And then you just continue on with two cells, and you can do this fully conservative. It also, as an AMR, when you do refinement, it drops to first order at this point. In the same way, it goes the other way around. We can also remove mesh generating points, and then distribute the conserved quantities to the cells that then fill up the volume. And so we usually do this actually more strictly than with AMR. So usually we set for kind of our zeros level, we set what we call a target gas mass. That's the mass the cells should have. And then once we are more than a factor of 2 away from this, we refine or de-refine. But in addition to this, same as AMR, we can also add any additional refinement criteria, right? So we can also refine on density or pressure gradients or in the outer layers.
Yeah. Thanks.
Yeah, so this, similar to AMR, you implement a second order volume scheme on this to calculate the fluxes. One difference that's I would argue interesting is that in AMR it actually has been demonstrated that you can, it's not trivial, but it's reasonably straightforward, go to higher order schemes. So ppm is slightly higher order, but you can also use a Wiener method or something to go to fourth order, whatnot. You can use discontinuous Galerkin, which is like just a different way of doing, slightly different way of calculating the fluxes and doing your discretization to go to essentially arbitrary order with AMR. This is, at least in practice, much harder with the unstructured mesh that's in a repo, and we have looked into this actually quite a bit, but we haven't really gotten anything that you can actually use for practical use. It has the same problem with coupling hydrodynamics to gravity as any other AMR mesh code. So again, you don't. This is where some energy error usually comes in, because this coupling is not perfect, and you, depending on whether you flow against, like down the potential or up the potential, you can get some kind of systematic error. Yeah, it's intrinsically Galilean invariant, because like at least if you start with the velocities of the cells as the gas velocity and then just do a correction that doesn't depend on the absolute velocity, then you can really show that, like, if you boost the whole thing, you really get essentially identical. One small downside of this is that because you move your mesh turning points around and you have these correction velocities, there's always some kind of noise on the mesh scale that you can beat down by doing this better, but there's always some kind of noise.
I've seen people claim that moving mesh is third order accurate for the angular momentum. Do you know, like, if this has been actually shown?
Who claims this? Like, I know that a repo isn't.
Yeah, I think in one of the Gizmo papers.
Gizmo. Okay, so then I wouldn't.
So what's the actual conservation of angular momentum if you use a repo? What's the actual conservation of angular momentum if you use a repo?
So fundamentally, it's also not perfectly conserved, as with any mesh code, right? So the fundamental reason why this is, well, there are several reasons, but one of them is that like you kind of have only one average velocity quantity in every cell, and you can essentially choose whether you conserve the linear or the angular momentum. And usually, linear momentum is deemed more important.
But has it actually been shown that it's only second order?
I know I've looked into this in test problems when repo initially was only first order, right? And so like I worked on this quite a bit to get it to second order. And so for something like the Yi vortex or so, also like all the things are second order, including the angular. I don't remember. I remember I looked at angular momentum. I don't remember it significantly better.
But can you quantify what's the like after actual simulations what it is?
Well, this depends a lot on the simulation, and so it depends depends a lot of practice. Like I don't think you can make any general statement as with the energy error, right? Resolution helps a lot, but in the end you need to monitor it, and then if it's above a certain relative value, you should just not trust your simulation. Also,
So in Eulerian codes, the lack of Galilean invariance at least comes partly because of the velocity dependence of the truncation error.
Yes.
And so if you're using mesh equations that aren't preserving it, making it exactly Lagrangian, is it still Galilean invariant in that case? And also, when you do the remapping, don't you introduce dissipation there that would also make it not invariant?
So we do for the, I think, yes. So the hardly true, but I don't like the way we do them. They do not write the Galilean invariance, right? So we have like the remapping, for example, introduces dissipation, but what it exactly does is like exactly like two machine precision independent of bulk velocity. So it will not change the Galilean invariance. Similarly, the Riemann solver actually that calculates the fluxes is a bit more tricky. And what we do there is that we calculate the fluxes in the moving frame of the interface. And this also kind of inherently guarantees you Galilean invariances. Like it's then slightly different things that you solved, and you can, in principle, also solve it in the lab frame and then like just add the advection term from the mesh movement. But then it wouldn't be a Galilean invariant. But it actually turns out that this is actually really better, mostly because you have this cancellation in the mass flux that's like very small, right? And so if you would do this in the lab frame, then you have a cancellation of two large terms. So, yeah. So we have also tested this quite a lot because it's one of the things that we, it's for debugging very helpful as well, right? Like, so if you have a problem and you're not entirely sure if there's an issue now or not, just boost it with a really high velocity that's like many times the sound speed, right? And it really shouldn't change. If it changes, then you screw up something. Yeah. Okay. Yeah, total energy and total angular momentum are only conserved approximately. One thing that's just a rough number, so in practice to get to reasonable energy conservation in the COM envelope, turns out we need to roughly resolve the pressure scale height by about 10 cells in the center of the simulation. Additional physics turns out to be much harder to implement than on an AMR code. That's in general not an issue with a moving mesh. It's just an issue with the unstructuredness of the mesh, right? Because the number of interfaces changes. There's no clear rule where your neighbors actually are, like relative to a cell, and so yeah, anything that makes a lot of solvers just like more tricky. It's also if you have issues with the regularization of the mesh, so if you get like distorted cells, that also makes a lot of these more complicated solvers much more unstable. So we seem to have this under control for magnetic fields nowadays, and also for radiation transport with some kind of with an M1 solver. But yeah, it's kind of, you have to spend much more effort in actually getting this to work. Also, for AMR codes, for most of these, like at least on this level of things, they're just recipes in literature of how to do this. While you can often use them as a starting point, but you still need to adapt them quite a bit to work on your structure. And yeah, in general, this comes back to the initial conditions as before. Modeling the surface of a star is much harder this is also true generally in mesh codes than with something like SPH. It's mostly because at the surface, you always have some kind of unresolved pressure gradient into the background. And so you just tend to smear out the surface. And the question is then, how and where can you actually stabilize the mesh codes? And this is also, there are a lot of tricky things going in there. And yeah, so we discussed this briefly in the simulation session or in the general session yesterday, that usually you have some like very thin and hot envelope in the outside, but that also like usually need to pay some price there as well. Very carefully try to understand what's going on there if you want to analyze it, for example, for optical display of the transits.
But it should be comparable to AMR, right? It's not that it's worse than AMR.
Yes. I completely agree. Right? It's a general problem of mesh codes. It's more. This is a big difference to how this works in SPH. Where in SPH the surface is in SPH the surface is more stable than you want it to be, and on mesh codes it's less stable than you want it to be.
So is it fair to say if you have constant mass elements, essentially the surface is completely unresolved because you can't resolve below a kernel worth of mass, right?
Wait, but what happens?
So I agree that stability is more challenging, and it comes back to your pressure scale height criterion. You have to resolve the pressure
So what happens in practice then in mesh codes is just like if you start with like a sharp jump in the pressure, it will just smear out the pressure, like it will just push out gas and smear this out until it's like resolved enough to actually be stable, right? To whatever this criterion on your surface actually is, and you will then just get like a smooth transition that is at this criterion, right? It roughly tells you how many cells you need. Yeah. So it's in general, so the moving mesh is kind of in between the AMR codes and the Lagrangian codes, right? So it's in some properties close to the Lagrangian codes, and in some properties close, or like from the kind of the hydro scheme in general, from a like discretization point of view, much closer. Okay, so this already brings me to my summary. I hope I could show you that like the different codes actually have like very different numerical properties, very different strengths and weaknesses. And in general, this is also like it's very like if you run a simulation with like two very different codes and get like quantitatively similar results, right? Then you can probably trust these results much more than if you would do this just with one type of scheme or with one type of code. Yeah, understanding the critical points of your problem is like kind of important to decide which code is optimal. And then also for this, you first need to know what actually the strength and the weaknesses are of your code or your scheme, and like where it actually works well and where it doesn't work so well. Yeah, there will be an open source version of Wrapper soon, hopefully in a few weeks. So yeah, like lots of people complained about limitations to availability of like moving mesh codes. This should be less of an issue then, hopefully. Although, yeah, like so we mostly spent we spent many months to clean up this code, like to clean up for the public version. It's still like much more complex than Gadget 2, right? So if you have not downloaded Gadget 2 as an SPH code and ran this, that's still way simpler than getting this to run. But we also added like this will have lots of examples and kind of test cases where you can set up like there's an example to set up a polytrop, so you can just see how to do this and how to do things with it. And yeah, so one of the things I thought about a little bit is that so one of the questions is always like, to which degree do you actually get rewarded if you go to higher order with your hydrodynamics? And so one of the problems is this is usually, or the main criteria from when this can help is usually how many discontinuities you have, right? Because discontinuities are fundamentally first order, jump. So if you have lots of shocks in your simulation or lots of like true discontinuities of like strong shear flows or so, then higher order doesn't help you too much because you drop down and all of these discontinuities to first order. However, the common envelope in general seems to be a smooth, or for most of the volume seems to be a smooth problem. And so if you have a smooth problem, then in principle, going to higher order can actually give you a much more efficient solution to a certain problem. So it would be interesting to look into to which degree that would actually be an interesting test case for higher order codes. Okay, that's it.
Moderating the discussion, I guess. We're running a little over time, so maybe we'll have a 15-minute discussion, and then we'll have a slightly overtime on the coffee break. Okay, so go ahead,
I would just make two small comments. One, I think AMR codes also have the big advantage, especially if they're block-based and good written like Athena, that if you measure speed as cells per second or particles per second for SPH, AMR codes are roughly an order of magnitude, in my experience, faster.
It's not that much fast, but it's faster, right?
Well,
because
it depends on the AMR method, I guess. Right, but the Athena is extremely fast, so they have this one advantage. And second of all,
so just one small sentence.
Yeah.
That's essentially because you know in which order which operations you need to do before, and because you know which interface is where and where it goes on the other side, right? While on the moving mesh, like in every time step, the topology of the thing is different.
well, that and you just the way computers work, you can vectorize much more efficiently.
Yeah.
But second thing is it's kind of a personal thing for me. I know a lot of people say that SPH is Lagrangian, but I'm not sure that's true because the smoothing kernel, whenever you actually want to calculate physical quantity, which is like a primitive density, you're actually taking all the neighbors into account. So you are mixing particles. So I wouldn't call it a truly Lagrangian scheme in that sense.
Yeah, I agree with the point, but I think it's like semantics.
It's semantics unless you have discontinuities.
I think what actually an interesting conceptual point, what's like much more critical with SPH is the fact that the kernel is always spherical.
Yeah.
Because if you think about what a true Lagrangian method do if you have a shear flow, right? Then it like kind of distorts like a certain mass element and just stretches it and so on, and then at some point you have a super complicated like shape of your mass element. But because the kernel is always spherical, you essentially remap the volume of your mass element in every time step to a sphere, without compensating for the exchange that you would do if you would kind of really go to the other volume.
Yeah, so I have two questions. Well, there are two things which I find very important for common envelope simulation. So first of them is angular momentum, because final orbital angular momentum of a fourth binary is usually less than a percent of initial angular momentum. And so my question is, if you will tell me roughly, like, what is the angular momentum conservation in a repo at the end of common envelope simulation, and how it compares to AMR, for me it will give whether I should start using a repo or not.
Yeah, so I would have to check the exact numbers in Sebastian's simulation. I can tell you later. I think it's percent or better. So I think the angular momentum is like. So we looked at this, and we usually were not worried. We're usually worried about the energy conservation. Right? So we usually stop the simulation when the energy error reaches 10%. And at this point, the angular momentum is still good for us.
I have a feeling that most of the errors come because of advection terms. The errors in angular momentum are because you have advection. They're not from the other terms. And since in these codes you have less advection, I think you would have less of an error. I'm not sure about the order, but there might be a difference in the prefactor.
Yes, no, I think they're both second order in angular momentum conservation, in my experience. But yeah, so the prefactor is slightly better.
And my second question is that, so I actually thought before that IMR, so the moving mesh is closer to SPH in terms of not having a boundary problem, but you said that they also have to deal with a hot vacuum or whatever it means. And the hot vacuum usually provides a problem with if you take the bigger box and you have to remove a bigger mass of the hot vacuum, and it also shapes whatever it is, whatever tries to be ejected from the common envelope event. So my question is that, is it comparable to RMR, or you can deal with a smaller mass or whatever? I mean, is it more stable if you provide less of a hot vacuum? I really don't like hot vacuum.
Nobody does.
I think in this it's like very similar to AMR. There might be slight differences that you probably have less diffusion on the surface as well. Like you smear less, because also in the surface, if it expands or contracts a little, it's mostly Lagrangian. But kind of the fundamental problem that you like somehow need to do something with the pressure gradient there is
Just your last point, I think, is a good one. I'll take issue, though, about I think there's a lot of shocks in common envelope evolutions, or a lot of discontinuities. I mean, certainly you see all the spiral shocks happening, during the later phases. But I agree that the higher order, because what's interesting.
Are you sure that for all of the simulations these are true shocks?
There are discontinuities and
Yeah, not only shocks, but discontinuities.
It's worse if they're not shocks, right? It's worse if they're contacts.
Yeah. But I think the point is that the higher order schemes, because the flows are both, it's unlike, things where you have nice planar shocks or a supernova shock, because you have both shocks and then a lot of mixing behind them. And so the higher order scheme, I mean, I think that's something really to understand as we go deeper, is that the mixing of the flows. Having a third order scheme would be great for keeping that stuff from getting diffused away.
Yeah, actually.
A lot of people.
So talking about these codes, in my work have compared three directly, perhaps the only time they're being compared side to side in this way. And what is interesting is, surprisingly, they give very comparable results when you do these comparisons, minus some issues with defining, say, resolution between AMR and SPH. But then you get lulled into a false sense of security, because then all of us have done things within our own codes, like changing parameters by a little bit and realizing that things are actually really weird. So I could tell you right now that resolution matters or doesn't matter as to the final separation, right? Sometimes you think, well, it's surprisingly invariant, but then you realize in other conditions that you change your AMR levels of refinement and you go deeper. So
It's worse, you can change the kernel for SPH, and that will affect your output.
well, I've actually tested that quite extensively, but on only one parameter set, right? And you change parameters, you go to master stars, everything really changes. So with reference to what we were talking about yesterday of, some master simulation that we all go to, I mean, I think that's advisable, but it's also questionable in that, you go to low mass, it's going to be really different. So I think this is a really great thing to achieve in these 3 days, to have some kind of guideline within which, it won't be perfect, but within which we can, I mean, it's really hard to decide what it is without huge amounts of work, which of course nobody has time for.
Just I'll comment also about this here. I think you or Natasha made this comment yesterday about like actually showing convergence. Because like kind of the zeros, like, and I think this is usually very expensive to do, so it's not done very often. But the zeroth requirement, I would argue, to actually make a point that there's some indication for convergence is if you have your standard simulation, you run it with a factor of 2 better spatial resolution and a factor of 4 better spatial resolution, right? So there's a factor of 8 and 64 in mass resolution. And then what you want to show is that the difference between the results actually gets smaller. And that would be an indication for convergence. It can still trick you completely.
Agreed.
But
Yes, so to follow up both on this point and something that I think you did a wonderful job highlighting is maybe something to keep in mind is that, as you say on that slide, that there isn't just one common envelope simulation, and that if we are as interested in a particular aspect of this big complicated problem, then there might be different tools that are more optimal, and it's sort of critical to prove that the aspect that we're most interested in at a given moment is there's indications that that's validated in the method that we're using. Not just that, like, I think that what Ursula's alluding to is that we just prove that we can do a test case and then go crazy. We haven't proved that the thing that we're trying to measure is also.
I agree. It also depends on which
thanks for highlighting that here.
It's usually people say that individual simulations.
More comment?
as well as codes.
Yeah. Well, I'll ask something. Maybe more so. You mentioned a little bit about hierarchy schemes. It's straightforward to do.
There's also human error.
Do you have any thoughts on how to write it? Obviously,
No, we actually
you guys have
we have worked with mathematicians for quite a while on this.
Right.
And so the main thing we actually are looking at there is the discontinuous looking.
Yep.
Where you kind of have higher order basis functions in a cell, and then you have like more information about the internal structure.
Right.
And then you also only need the direct neighbors to calculate the synapses. The main problem, and this is mathematically like turns out to it quickly becomes tricky, is that one of the fundamental assumptions of discontinuous Gaussian is that you split the problem into basis functions that only depend on the spatial structure, and then coefficients that give you like weighting for these spatial functions that evolve with time. Now, if the mesh changes in every time step, then the first assumption is immediately broken.
Right.
And so you need to also evolve these basis functions, and that can become very, very tricky. In particular, to not lose order with this thing, right? Like, so then you really need to like kind of time resolve smoothly how the topology of the mesh changes during a time step. This is very tricky.
Okay, then second question related to that. Usually when you do high order schemes spatially, you should also need to do high order schemes in time as well. Now, in moving mesh codes, this comes at a high price because one of the things that you show, right, was that basically you do not account for the mesh motion during your scheme, you're going to get first order results, right? Right. So if you go to higher order schemes, you have to basically essentially reconstruct the point on the mesh more time per time step. And so the question is that worth cost versus basically just drawing just for the channel?
But I think, well, for second order at least, yeah, you've shown you can still do it with one mesh construction here. And I think Ilat claims that, or
Yeah.
principally for arbitrary order, you can still
You
do
can,
it.
but it won't be so stable. So the thing is, if you do like a run credit time step,
Yeah.
forget the formal definition of it. There's like a stable way and unstable way. The stable way, I mean, is that your end product is just a weighted summation of different states, and there's like the midpoint method where you take fluxes from one subcycle and but the conserved variable is from a different. So this unstable, I found a way where you can do only one mesh construction actually,
Okay.
and go to arbitrary high time steps. But it's not so stable in my experience. The only way to get it to actually be stable is to actually do more mesh constructions.
All right.
Yeah.
I see. So you have to linearly interpolate then in order to get the, because basically it's a question like what are the other order fluxes basically? So you have to interpolate in order to get other fluxes, the other substeps.
So like every time step, you just do the fluxes.
But
Calculate.
using the original mesh.
Either the original mesh or the mesh at the end of the time step.
So your mesh check jumps in the middle of the time step for the old previous.
Right. So basically, you start with your first order time step, then you construct the mesh for the next time step, and then you calculate new conserved variables, calculate fluxes on it, evolve again. You keep on using the old mesh, but just changing the conserved variables, or either the old or the new one.
Okay. And that actually is higher order time.
Yeah.
Really? Okay.
Yeah, formally it should give you, right?
Yeah.
But one thing I think that's in general interesting about this is that if you go to higher order, it seems to be much more critical to do this in space than in time. So
Yeah.
even if you do like high order DG or so,
Yeah.
if you can go to like fifth, sixth, or I think we have tried fourth order, but you don't like your error still like your your absolute error still goes down a lot without going to necessarily equal time integration.
Okay.
So Adam was right that, shocks are important as well as smooth flow where you get turbulence, and that obviously can be important for energy transport. But so I was wondering to what extent you think that variable order schemes like WINO would be a good direction to go rather than a fixed order with DG or something like that.
But also with DG, you can in principle
You
do
can vary the order.
EU refinement, right? Just decide for every cell to which order.
Uh-huh.
I think the problem really comes down to like what kind of the typical volume fraction of your discontinuities is, right? And so if you, of course, you want to then go, you automatically go and you try to take this to go to lower order where you have these discontinuities. But if you think about if there's regularly some discontinuities sweeping over your like high order solution, not much of it will be left, right? Like you will just like lose information there. So I think it's really the question is like how much does this interact and so.
Well, presumably that's not such a problem with moving mesh schemes, right? Because discontinuity moves with the mesh, right?
No, it guesses.
Oh, sure, right. You're right. Yeah.
So that's for shocks that doesn't work. For shear flow that might still be okay.
That's true. Contact would, but a contact would. But
Yeah,
not
contact is much better. Yeah, contact is just general the moving mesh much better than for a given resolution you just get much less
Yeah.
issues there. But yeah, shocks are.
Well, okay, I could talk to you about it later. I mean, there are test problems that do have shocks going through smooth material that schemes like WINO seem to do well on.
Yeah.